For months, astronomers watched it glide through the dark, a cold traveler from another star. Harmless, ordinary, forgettable. But by November 2025, everything changed. New data showed 3 Atlas wasn't drifting past the solar system. It was aiming its new course straight toward the Jovian system, the realm of Jupiter, the giant of storms. On March 16, 2026, it will pass within just 54 million kilometers of the planet, close enough to be captured, changed, or to change something else entirely. And scientists can't decide whether to celebrate or panic, because Jupiter's system is no ordinary destination. It's a trap for comets, a cradle for moons, and some believe the perfect environment for capturing or seeding material capable of sustaining or generating life. Is this a coincidence or intention? Stay until the end, because tonight we follow 3 Atlas's trail from the first telescope sighting to the edge of Jupiter's shadow. And by the end, we reveal why Jupiter might not just be its target, but may have been the mission all along. And if this mystery continues to have you on the edge the way it does me, don't just sit in the shadows. Make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and what you think about this new development. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this. So thank you for having our back. Part 1. The visitor that wasn't aiming for us. Something arrived from beyond the stars on July 1st, 2025, and it wasn't looking at us. The Asteroid Terrestrial Impact Last Alert System, known as ATLAS, picked up a faint smudge moving through the constellation of Achis, and within hours astronomers realized they were staring at something that had traveled for millions of years through the void between star systems. They named it 3 Atlas, the third confirmed interstellar visitor to our solar neighborhood. And for a few days, it felt like just another cosmic footnote, another rock from somewhere else passing through on its way to nowhere in particular. Except this one had a destination. Initial trajectory calculations showed the standard hyperbolic orbit you'd expect from an interstellar interloper. The telltale curve that says this object didn't form here, didn't originate in our gravitational family. Its velocity alone confirmed the story. Tens of kilometers is far too fast to be bound to our sun. The orbit bent around our star like a whip crack, and every astronomer who looked at the preliminary data assumed it would do what interstellar objects do: swing past the inner solar system, maybe give us a nice show if it developed a tail, then vanish back into the cosmic ocean from which it came, headed toward the general direction of the Milky Way's bulge, somewhere in the tangle of ancient stars near the galactic core, a traveler from one of those older neighborhoods slipping through our backyard on its eternal journey. But then the refinement started coming in. More observations, better data, orbital mechanics calculated and recalculated with increasing precision. By late summer of 2025, the picture had changed dramatically. This wasn't just a random flyby. The trajectory projections placed 3 Atlas on a long-term course that would take it directly through the outer solar system, and specifically toward Jupiter, not near Jupiter in some vague astronomical sense, toward Jupiter with an intimacy that made scientists check their math twice, then 3 times. The closest approach would occur on March 16, 2026, roughly 54 million kilometers from the giant planet itself, about 0.358 astronomical units. To put that in perspective, that's closer than Mercury ever gets to the Sun. For an object that originated light years away, traveling through unimaginable distances of empty space to arrive in our solar system, and then align its path so precisely with the largest gravitational well available. Well, that makes people nervous. Why does this matter? Why should anyone care about a chunk of ice and rock getting near Jupiter when Jupiter gets hit by things all the time? Because Jupiter isn't just a planet. It's a cosmic trap, a gravity well so immense that it reshapes the trajectories of everything around it. Its magnetosphere extends millions of kilometers into space, invisible bubble of charge particles and magnetic field lines that can capture dust, gas, and whatever else wanders too close. And circling this giant are some of the most scientifically interesting moons in the entire solar system. Europa, with its subsurface ocean locked beneath kilometers of ice. Ganymede, the largest moon anywhere with its own magnetic field. Callisto, ancient and crater-scarred, possibly harboring liquid water beneath its crust. These moons represent some of the best candidates for life beyond Earth that we know of. Protected oceans, energy sources, chemical complexity, everything you'd need for biology to take hold. If only it had the right ingredients to work with. Now imagine an interstellar object, one that has been soaking in cosmic radiation and accumulating complex organic molecules for eons, arriving at precisely the right angle and speed to interact with this system. Not crashing into Jupiter itself, where everything would be incinerated in the atmosphere, but threading the needle between capture and escape, potentially depositing material onto those moons or into the magnetosphere where it could alter the chemistry of an entire planetary system. This is the fear that keeps a growing number of researchers awake at night. Not that 3I Atlas will hit Earth. It won't. Our planet isn't even in the conversation. The fear is that Jupiter might be the actual target. And if this object is carrying the building blocks of life, or in more speculative scenarios, something even more intentional, then its arrival in March of 2026 might not mark the end of a long journey. It might mark a beginning, the seeding of life in a new environment, delivered by a courier that has been traveling since before our species existed. We've always assumed that interstellar objects just wander randomly, victims of galactic currents and gravitational perturbations. But what if some of them don't? What if just once in a while they're aimed? Part 2. The mathematics of an impossible alignment. The orbit of 3I Atlas reads like a carefully plotted course, and that's what makes it so unsettling. After its discovery in early July of 2025, astronomers began the painstaking work of calculating where it had been and where it was going. These calculations aren't simple. You have to account for the gravitational pull of the sun, the subtle tugs from planets, even the outgassing forces that occur when a comet heats up and releases jets of vapor. Every factor matters when you're trying to predict the path of something moving at cosmic velocities. The inbound leg of the journey brought 3 Atlas from the outer reaches of the solar system, diving toward the warmth of the inner planets. Its perihelion, the closest point to the Sun, would occur in late October of 2025 at approximately 1.4 astronomical units, just inside the orbit of Mars. This is where things get interesting for comets. This is where they wake up. At that distance, solar radiation begins to sublimate the frozen volatiles locked in the nucleus. Water ice turns to vapor. Carbon dioxide and carbon monoxide begin to boil off. Dust particles trapped in the ice for perhaps billions of years suddenly find themselves freed and pushed away by the pressure of sunlight. A coma forms, a fuzzy cloud of gas and dust surrounding the solid core. Sometimes a tail develops, streaming away from the sun like a banner in Thessaly wind. But 3 Atlas isn't just making a quick pass around the sun and leaving. Its outbound trajectory takes it back out toward the outer solar system. And this is where the orbital mechanics become genuinely strange. The path curves outward, accelerating as it leaves the sun's influence. But instead of heading towards some random point in space, it's heading toward Jupiter. The encounter on March 15th or 16th, depending on exactly how you calculate it, will bring the object to within approximately 0.358 astronomical units of Jupiter's center. That's roughly 53.6 million kilometers. An astronomical unit is the average distance between Earth and the Sun, about 150 million kilometers. It's a convenient yardstick for measuring distances in the solar system. When astronomers say 0.358 AU, they're describing a proximity that's uncomfortably close on solar system scales. Jupiter's Hilsphere, the region where its gravity dominates over the Sun's, extends much farther than that. Any object passing that close is entering Jupiter's domain, subject to its immense gravitational influence. Now, here's where the statistics get uncomfortable. Researchers, including A.V. Lowe and colleagues, have calculated the probability of an interstellar object randomly entering our solar system and just happening to align its trajectory so precisely with Jupiter's location. The numbers vary depending on the assumptions you make about the object's origin and velocity distribution, but some models suggest probabilities as low as 0.04%, less than 1 in 2,000. That's not impossible. Rare things happen. Roll a 20-sided die enough times, and eventually you'll hit any number you want. But this isn't a casino. This is the universe. And when something that unlikely occurs, scientists pay attention. They ask questions. Could there be selection bias? Maybe we only notice the interstellar objects that do something interesting. and we're missing all theons that pass through unremarkably. Could there be physical mechanisms we don't understand? Maybe the galactic environment preferentially ejects objects in certain directions, creating pathways through interstellar space that are more likely to intersect with planetary systems. Or could the alignment be intentional? This is the question nobody wants to ask out loud, but everyone thinks about in quiet moments. Could an object modify its trajectory, using outgassing jets timed and oriented to produce thrust? Could it use non-gravitational accelerations to steer itself over millions of years, making tiny corrections that add up to a precisely targeted arrival? The mechanics of gravitational capture are complex, but well understood. If an object approaches Jupiter fast enough, it will whip around the planet and slingshot back out to space, gaining or losing speed in the exchange. This is how we send spacecraft to the outer solar system. We use Jupiter as a gravity assist, stealing a tiny bit of its orbital momentum to accelerate our probes. But if an object approaches at just the right speed and angle, if it's moving slowly enough, or if it loses energy through interactions with Jupiter's atmosphere or magnetosphere, it can be captured. It can become a moon, at least temporarily. The odds of temporary capture are low, but not zero. Jupiter captures objects occasionally. We've observed it with small asteroids that orbit for a few years before being ejected again. But those are local objects born in our solar system. 3 Atlas came from somewhere else entirely, and yet its trajectory suggests an awareness of where Jupiter will be when it arrives. The timing, the angle, the velocity, all of it fits uncomfortably well with what you design if you wanted to maximize interaction time with the Jovian system. There's also the possibility of gravitational resonances, where the object's orbit becomes synchronized with Jupiter's in some mathematical ratio. These resonances can stabilize orbits that would otherwise be chaotic. They're common in the asteroid belt, where countless rocks are trapped in stable configurations relative to Jupiter's 12-year orbit around the Sun. Could 3 Atlas be entering such a resonance? Could it be planned to do so? The alternative explanation is that we're just lucky. We happen to discover an interstellar visitor during the rare moment when one happens to pass near our largest planet. It's a coincidence, nothing more, and we should be grateful for the scientific opportunity it presents. Most researchers genuinely believe this. The universe is large, and strange alignments occur with no deeper meaning. But a small and growing number of scientists aren't satisfied with that answer. They look at the trajectory, they calculate the probabilities, and they wonder, if you wanted to send something to Jupiter, if you had millions of years to plan the journey and the ability to make small course corrections, this is exactly the kind of approach you would design. Close enough for meaningful interaction, fast enough to avoid immediate capture unless you wanted it, timed to arrive when multiple moons are in favorable positions for material deposition. The question isn't whether 3 Atlas could be aimed at Jupiter. The question is whether we'll know if it was. Part 3. When comets stop acting like comets. Comets are supposed to be predictable. We've been studying them for centuries, watching them light up the night sky as they round the Sun, and then fade as they retreat back to the cold outer regions of the solar system. We know their rhythms. We understand their chemistry. Frozen water, carbon dioxide, carbon monoxide, various organic compounds, all locked together in a dirty snowball that spends most of its existence in the deep freeze of space. When the Sun's heat reaches them, they respond in ways we can forecast with remarkable precision. 3 Atlas is not following the script. The first anomaly that caught astronomers' attention wasn't just that it had jets-off outgassing. That's completely normal for comets. It was that these jets appeared sustained and directional in ways that raised eyebrows. When a comet approaches the Sun, its nucleus heats unevenly. The side facing the Sun warms faster, causing volatiles there to sublimate and create jets that push material away from the surface. These jets aren't random. They're tied to the rotation of the nucleus and the location of volatile rich patches. Over time, as the comet rotates, the jets sweep around like lighthouse beams. But observations of 3 Atlas showed jets that seemed persistently oriented, possibly toward the Sun, or even in some analyses with components that aligned disturbingly well with the direction of Jupiter. This matters because jets create thrust. Every time a comet releases a plume of gas and dust, it's essentially firing a tiny rocket engine. The force is small, but in the vacuum of space, small forces applied consistently over long periods can significantly alter trajectories. Scientists call these non-gravitational accelerations, and they're crucial for predicting exactly where a comet will be months or years in the future. The math works both ways. You can observe where a comet goes and back-calculate how much force the jets must be producing. For 3I Atlas, those calculations produced uncomfortable results. The amount of thrust in its direction suggested outgassing patterns that would be unusual, but not impossible for a natural comet. Or if you squint at the data differently, patterns that would be consistent with deliberate trajectory corrections. Then there's the chemistry. Early spectroscopic observations of 3I Atlas revealed something genuinely strange. The ratio of carbon dioxide to water vapor in its coma was approximately 8.1, much higher than typical comets from our solar system, which usually show ratios closer to 1.1 or even lower. This suggests the object formed in an environment where carbon dioxide was more abundant than water ice, or where water ice was somehow depleted. That's possible in the outer regions of another star system where temperatures and chemical conditions differ from what we experience here. But the real alarm came with the detection of nickel emissions in the comet spectrum, with little or no corresponding iron signal. This is highly unusual. In normal solar system objects, nickel and iron appear together because they produce together in stellar nucleosynthesis and remain associated through planetary form. Finding nickel without iron is like finding smoke without fire. It suggests either an extremely exotic formation environment, or in more speculative interpretations, some kind of processing or refinement of materials that shouldn't occur naturally in comets. Some researchers have noted that nickel tetracarbonyl, a volatile compound of nickel and carbon monoxide, could potentially explain the observations. This compound forms under very specific conditions and is so unusual in natural astronomical settings that its presence would demand explanation. Industrial chemistry on Earth uses nickel carbonyl in refining processes, but finding it in a comet would imply chemical pathways we don't normally see in nature. The morphology of 3I Atlas added another layer of strangeness. Astronomers observed not just a normal dust tail which points away from the sun due to radiation pressure, but also features that looked like anti-structures that appear to point toward the sun. Anti aren't impossible. They can form when Earth's orbital motion causes us to see the dust trail from a particular angle, creating the illusion of a sunward-pointing tail. But in 3I Atlas, the anti-tail features persisted and evolved in ways that suggested active dust release with unusual geometry. All of these anomalies individually have possible natural explanations. Comets from other star systems might simply behave differently than ours. They formed in different chemical environments, orbited different stars, experienced different radiation histories. We've only studied 3 confirmed interstellar objects: Oumuamua, 2I Borisov, and now 3 Atlas. That's not enough to establish what's normal for the interstellar population. Maybe they're all weird in their own ways, and we just don't know it yet. But when you stack the anomalies together, when you add up the unusual trajectory, the directional jets, the exotic chemistry, the morphological oddities, you start to get a picture that makes some scientists uncomfortable. A small minority, including Avi Lobo, have publicly discussed the possibility that 3I Atlas might not be entirely natural. Maybe it's a probe. Maybe it's a vessel designed to carry something across interstellar space. Maybe it's been steering itself using its outgassing, not just as a byproduct of solar heating, but as a propulsion system refined over millions of years of travel. The mainstream scientific community treats these ideas with appropriate skepticism. The burden of proof for extraordinary claims is high. And so far, 3 Atlas still fits within the boundaries of what we'd expect from a natural interstellar comet, even if it's at the extreme edge of those boundaries. Most astronomers are confident that further observations will reveal natural explanations for all the apparent oddities. But there's a reason this object keeps making headlines. There's a reason mission planners are scrambling to point every available telescope and spacecraft at it. Because even if the probability of artificiality is low, the implications, if true, are so enormous that we can't afford to ignore the possibility. And because whether it's natural or not, 3I Atlas is heading toward Jupiter, carrying whatever materials it accumulated during its long voyage through space. If those materials include complex organics, if they include the chemical precursors to life, If they include anything that could catalyze biological processes in the subsurface oceans of Europa, or Ganymede or Callisto, then what happens in March of 2026 might be the most significant astrobiological event in human history. And we'll either be watching with every instrument we can bring to bear, or we'll miss it entirely because we convinced ourselves it was nothing special. Part 4. The target is a garden. Jupiter is not just a planet. It's an ecosystem unto itself, a miniature solar system with its own family of worlds, each one strange and compelling in ways that still surprise us decades after we first visited them. The giant itself is a rowing ball of hydrogen and helium with no solid surface, nothing but increasingly dense gas pressing down into exotic states of matter under pressures that would crush any spacecraft we could build. We can't land on Jupiter. We can barely survive in its atmosphere for more than a few minutes before the heat and pressure destroy our instruments. But the moons are different. They're solid worlds with histories written in their surfaces. And beneath those surfaces, some of them hide oceans, not frozen oceans. Liquid water kept warm by tidal heating from Jupiter's immense gravity. As these moons orbit the giant planet, Jupiter's gravitational field flexes them, squeezing and releasing them like stress balls in a giant's hand. That flexing generates heat through friction, enough heat to melt ice and maintain liquid water. Even though these moons orbit far from the sun, where temperatures should keep everything frozen solid. Europa is the most famous of these ocean worlds. Its surface is a shell of water ice, crisscrossed with cracks and ridges that tell stories of geological activity. Beneath that shell, maybe 10 to 15 kilometers down, lies an ocean that could contain twice as much water as all of Earth's oceans combined. That ocean is in contact with a rocky mantle below, meaning there's potential for chemical interactions between water and minerals, the kind of chemistry that could provide energy for life. We've detected what might be plumes of water vapor erupting from Europa's surface, suggesting the ocean isn't just sitting there stagnant, but is actively exchanging material with the surface and potentially with space. Ganymede is even larger than Mercury, the biggest moon in the entire solar system. It has its own magnetic field, the only moon known to have one, which creates a mini magnetosphere nested inside Jupiter's larger one. This matters because magnetic fields can protect against radiation, and the Jovian radiation environment is brutal. Ganymede also likely has a subsurface ocean, though it might be sandwiched between layers of ice in a more complex structure than Europa's. The presence of both a magnetic field and liquid water makes Ganymede exceptionally interesting from an astrobiology perspective. Callisto is the outermost of the large moons. Far enough from Jupiter, the tidal heating is weaker. Its surface is ancient, heavily cratered, telling us it hasn't been geologically active in billions of years. But even Callisto might have a subsurface ocean, though it would be deeper and colder than Europa's or Ganymede's. Some scientists think Callisto represents our best shot at finding pristine ancient material in the Jovian system, a world that hasn't been churned and recycled the way the inner moons have. These moons represent some of the best opportunities in the solar system to find life beyond Earth, or to understand the conditions necessary for life to begin. They have liquid water, they have energy sources, they have chemical complexity. What they might lack is the initial spark, the organic molecules and chemical building blocks that could jumpstart biological processes. Earth had those molecules. We think they accumulated from comets and asteroids that bombarded our young planet billions of years ago, delivering water and organics that eventually led to the chemistry we call life. Now consider what happens if an interstellar object carrying materials from another star system enters the Jovian realm. If 3 Atlas passes close enough to Jupiter, several scenarios become possible. The most straightforward is a simple flyby, where the object whips around Jupiter and continues on its way, leaving nothing behind. But that's not the only option. If 3 Atlas is actively outgassing during its approach, if it's releasing dust and gas as its ice seas sublimate, some of that material could be captured by Jupiter's magnetosphere. The magnetosphere extends millions of kilometers out from the planet, far beyond the orbits of the inner moons. Charged particles, dust grains, molecules, all of these can become trapped in the magnetic field, spiraling along field lines and eventually impacting the surfaces of the moons or being injected into their thin atmospheres. If the object passes close enough and slow enough, there's an outside chance of temporary gravitational capture. 3 Atlas could become, even if only for a short time, a moon of Jupiter itself. This would dramatically increase the duration of its interaction with the system, allowing more time for material exchange, more opportunities for dust and gas to settle onto the surfaces of the existing moons. There's also the possibility of fragmentation. If tidal stresses become too great, as 3I Atlas approaches Jupiter, the object could break apart. We've seen this before. Comet Shoemaker Levy 9 fragmented under Jupiter's tidal forces and then crashed into the planet in a spectacular series of impacts in 1994. If 3 Atlas fragments, some pieces might impact the moons directly, while others could create debris clouds that slowly settle over time. Any of these scenarios could result in the deposition of interstellar material onto the surfaces or into the subsurface oceans of Jupiter's moons. If that material includes complex organic molecules, amino acids, nucleotides, any of the chemical building blocks of life, then we're not just observing an astronomical event. We're potentially witnessing the seeding of life in a new environment. The chemistry would be subtle at first. Organic molecules landing on the icy surface of Europa wouldn't immediately create bacteria, but they would provide raw materials that weren't there before. If some of those molecules found their way through the ice to the ocean below, if they entered an environment with liquid water and energy sources and mineral surfaces for catalysis, then chemical evolution could begin. Not life yet, but the complex chemistry that might eventually lead to life given enough time. This is the scenario that keeps astrobiologists up at night. Not because it's likely, but because it's possible, and because the implications are staggering. We've always assumed that if life exists on Europa or Enceladus or any other ocean world, it either originated there independently or hasn't originated at all yet. The idea that life could be seeded from outside, delivered by interstellar couriers, changes everything. It means life might not need to originate on every world where it appears. It might only need to originate once somewhere and then spread. But there's a darker consideration too. What if the material 3I Atlas is carrying isn't just random organic molecules? What if in some sense that's hard to fully articulate, it's been prepared, selected, concentrated, packaged in a way that maximizes the chances of chemical evolution or even direct biological activity? What if this object has been traveling for millions of years with Jupiter's system as its destination, carrying a payload designed to catalyze life in environments exactly like Europa's ocean? That starts to sound like science fiction. It starts to invoke ideas of directed panspermia, Vanscient civilizations sending the seeds of life across the galaxy. Most scientists will tell you that's wildly speculative, that we have no evidence for anything like that natural processes are more than sufficient to explain what we're seeing. But they'll also tell you that if you wanted to see life on another world, if you had the technology and the patience and millions of years to work with, this is exactly how you might do it. You'd send your payload on a trajectory that intersects with a promising planetary system. You'd aim for the giant planet with its protective magnetosphere and family of water-rich moons. You'd time your arrival for when the object is outgassing, naturally dispersing your payload into the environment where it needs to go. And you do it in a way that looks entirely natural, like a comet doing what comets do, so that any observers would see nothing more than an interesting astronomical phenomenon. Whether that's what's happening with 3I Atlas is anyone's guess. But as March 2026 approaches, as this object draws closer to Jupiter, the question stops being purely academic. Because if there's even a small chance that we're witnessing a seeding event, we need Toby watching. We need to understand what's being deposited and where. We need to think about what it means for the future of life in our solar system. The garden might be about to receive a delivery from a very old, very patient gardener. Part 5, the window is closing. Time matters in astronomy more than people realize. We often think of space science as patient, methodical, willing to wait decades for the right moment. And in many ways that's true. But when it comes to interstellar objects passing through our solar system, patience is a luxury we don't have. These visitors move fast, stay briefly and leave forever. If we want to study them, if we want to understand what they're made of and where they came from and whether they pose any kind of opportunity or threat, we have to act now, not next year, not when the funding comes through now. 3 Atlas was discovered on July 1, 2025. Its perihelion, the closest approach to the Sun, occurred in late October of that same year. The Jupiter encounter is scheduled for March 16, 2026. That gives us from discovery to the main event less than 9 months. 9 months to mobilize telescopes, plan observations, analyze data, and potentially redirect spacecraft that are already in orbit around Jupiter or could reach the Jovian system in time. The challenges are immense. Most of our deep space missions were designed and launched years or even decades before we knew 3 Atlas existed. We can't just spin up a new mission on 9 months' notice. Building a spacecraft takes years. Testing takes months. Launch windows depend on orbital mechanics that don't care about our urgency. By the time we could design, build, and launch something specifically for 3I Atlas, it would be long gone. So instead, mission planners are looking at what we already have in the sky. The Juno spacecraft has been orbiting Jupiter since 2016, studying its atmosphere, magnetic field, and auroras. Juno is in a highly elliptical orbit that brings it close to Jupiter's cloud tops and then swings it far out into space before returning. That orbit was carefully designed for its primary mission, but it's not optimized for intercepting an incoming comet. To direct Juno toward 3I Atlas would require a significant burn, a change in velocity called delta phi in orbital mechanics. Calculations suggest that a maneuver executed on September 9, 2025, could alter Juno's trajectory enough to bring it near the comet during the March encounter. The delta V required would be approximately 2.675 km/s, which is substantial. It's not clear if Juno has enough propellant remaining to make such a burn, especially since the spacecraft has already been operating well beyond its original planned mission lifetime. Even if Juno could make the maneuver, there's a question of risk versus reward. Redirecting the spacecraft toward an unknown comet could shorten or end its primary science mission at Jupiter. The trajectory change might place it in a less favorable orbit for studying the planet itself. There's also the risk of collision with debris. If 3I Atlas is shedding large amounts of dust and ice, mission planners would need to balance the scientific value of a close encounter with 3 Atlas against the loss of ongoing Jupiter observations. Another option is the Jupiter Icy Moons Explorer, or JUICE, a European Space Agency mission launched in 2023. JUICE is currently on its way to Jupiter with arrival scheduled for July of 2031. That's too late for the initial 3I Atlas encounter, but depending on the object's behavior, there might be opportunities for JUICE to study lingering effects in the Jovian system. If 3I Atlas deposits material onto the moons or creates a debris trail that persists for years, JUICE could analyze those deposits and provide crucial data about the object's composition. There's also the possibility of coordinated ground-based observations. Every major telescope on Earth and in orbit around Earth can be pointed at 3 Atlas during key phases of its journey. Spectroscopy can reveal the chemical composition of the coma and tail. Photometry can track changes in brightness that might indicate rotation or fragmentation. Radio telescopes can search for any signals, though most scientists emphasize this is purely for thoroughness and not because anyone seriously expects to find transmissions. The International Asteroid Warning Network, a group coordinating observations of potentially hazardous objects, has already flagged 3I Atlas for continuous monitoring. While the object poses no threat to Earth, its unusual characteristics and trajectory make it a high-priority target for study. Observing campaigns are being organized to ensure continuous coverage as the comet moves through different regions of sky, visible from different locations on Earth. But all of this depends on timing. The window for making decisions about spacecraft maneuvers has already mostly passed. If Juno was going to be redirected, that decision needed to be made months ago. Ground observations can continue right up until the encounter and beyond. But the quality and type of data we can get from Earth are limited compared to what a spacecraft at close range could provide. This raises uncomfortable questions about preparedness and priority. If 3 Atlas really is something extraordinary, if it's carrying materials or information that could transform our understanding of life in the universe, are we doing enough? Should we be taking bigger risks with our existing missions to study it? Should we have emergency protocols for rapid response to discoveries like this? On the flip side, if 3 Atlas is just an unusually interesting natural comet, Is it worth potentially sacrificing ongoing research at Jupiter to get a closer look? Scientists make these kinds of trade-off decisions all the time, weighing the value of different observations, deciding where to point limited resources. But the consequences feel weightier when you're talking about an object that came from another star system and might never be seen. Again, some researchers have pointed to this situation as evidence that we need better infrastructure for studying interstellar objects. Dedicated spacecraft parked in the outer solar system, ready to intercept visitors on short notice. Improved early warning systems that can detect and characterize these objects sooner, giving us more time to respond. Faster decision processes that don't require years of committee meetings and budget approvals before taking action. These are all valid points, but they don't help us with 3 Atlas. This object is here now, following a trajectory we can predict, with increasing accuracy, heading toward an encounter that will happen whether we're ready or not. March 16, 2026 is coming. Jupiter doesn't care about our mission constraints, or our funding cycles, or our debates about scientific priorities. The question we face is simpler and more immediate. Will we be watching when 3 Atlas makes its closest approach? Will we have instruments in position to measure what happens? Will we collect the data that could answer, or at least inform the questions about whether this object is natural? Whether it's targeting Jupiter, whether it's carrying materials that could affect the biological potential of those distant moons? Or will we miss it because we weren't quite ready, weren't quite fast enough, didn't quite believe it was important enough to justify the effort and expense? The window is closing. Every day that passes is a day we can't get back. And once 3I Atlas swings past Jupiter and continues on its way back into interstellar space, it won't be coming back. Whatever secrets it carries, whatever implications its journey holds, we get one chance to study it properly. The universe isn't going to give us a second opportunity just because we weren't prepared the first time. This is it. This is the moment. And the people making decisions about telescopes and spacecraft trajectories right now are determining whether future historians will look back on 2026 as the year we learned something profound about our place in the cosmos, or the year we let the most interesting visitor in human history slip through our fingers because we didn't act fast enough. Part 6. The mathematics of steering a comet. When you watch a comet move across the sky, you're seeing something that appears passive, a chunk of ice and rock subject entirely to the laws of physics, pulled by gravity, pushed by sunlight, moving on a path determined by forces beyond its control. And for most comets, that's exactly right. They're not driving themselves. They're falling through space, following trajectories shaped by the gravitational pull of the sun and planets, occasionally perturbed by the odd rocket effect of their own outgassing, but not in any controlled or directional way. But the math tells a different story when you look closely. Every time a comet releases a jet of gas and dust, it creates thrust. The principle is simple. Action and reaction. Newton's third law. Push material in one direction, and the object moves in the other. The force is tiny compared to what we're used to from rocket engines. For a comet jet might produce thrust measured in Newton, thousands of times weaker than a human breath. But in space, tiny forces add up. The key is persistence and direction. If a comet nucleus has active vents on one side, and if those vents fire consistently, when that side faces the sun, the cumulative effect over months or years can shift the orbit by noticeable amounts. Astronomers have to account for this when predicting where comets will be. We call it non-gravitational acceleration, and it's been measured in dozens of comets from our own solar system. For 3 Atlas, scientists observed jets that appeared more sustained and directional than you'd typically expect from random surface features. The outgassing wasn't just a consequence of solar heating, creating temporary vents that opened and closed as the nucleus rotated. There seemed to be preferred directions, orientations that persisted longer than simple rotation models would predict. To understand what this means, you have to think about how jet patterns evolve. When a fresh comet approaches the sun for the first time, its jets are chaotic, firing from wherever volatile ice happens to be near the surface. But over multiple passes, the surface gets processed. Less volatile materials accumulate, forming an insulating crust. Active areas become localized to specific vents or fissures where fresher ice is exposed. The jet pattern becomes more consistent, more predictable. 3 Atlas hasn't been through our solar system before. It's an interstellar visitor on its first and only pass through our neighborhood. So its jet behavior should be chaotic first-timer behavior. Instead, we're seeing patterns that look almost evolved, as if the object has learned how to manage its outgassing. That could have natural explanations. Maybe the surface got processed during passage near another star millions of years ago. Maybe interstellar radiation created a crust that channels volatiles through specific weak points. Maybe we're just seeing random vents that happen to align in ways that look significant. Or maybe, and this is the part that makes people uncomfortable, the jets are oriented deliberately. If you wanted to steer an interstellar object over millions of years, using outgassing as your propulsion system, you'd need to control when and where the jets fire. You'd need active vents positioned at specific locations on the nucleus, releasing material at calculated times to produce thrust in the desired direction. The technology required wouldn't be rockets, as we understand them. It would be more subtle, perhaps engineered pockets of volatiles that sublimate at specific temperatures, creating thrust when the sun's heat reaches a certain intensity. Perhaps surfaces designed to channel outgassing in particular directions, like nozzles carved into ice. The amount of delta V change in velocity that you could generate this way is limited but sufficient. Calculations by Avilo and colleagues suggest that even modest non-gravitational accelerations applied consistently over the years' long journey through the solar system could account for the trajectory alignment we're observing with Jupiter. You don't need powerful engines. You need patience and precision. Here's where the statistics become truly uncomfortable. When researchers model the trajectory of 3I Atlas and work backward, asking what forces would be required to shift a random hyperbolic orbit into the observed Jupiter targeting trajectory, the numbers aren't impossible, but they're specific. The jets would need to fire with particular timing relative to the sun's heating. The thrust would need to be oriented not just away from the sun, which is natural, but with components perpendicular to that direction, creating sideways pushes that curve the orbit. Some models place the probability of this occurring naturally at around 0.04%, though others suggest slightly higher odds depending on assumptions about the velocity distribution of interstellar objects and the geometry of their orbits. What's consistent across models is that this is rare. Not 1 in a million rare, but 1 in thousands rare. Rare enough that seeing it happen suggests either extraordinary luck or something more deliberate. To put that in context, if interstellar objects pass through the inner solar system at a rate of roughly 1 per year, which is a rough estimate based on the detection rate of Oumuamua, 2I Borisov and now 3I Atlas, then we'd expect to see a Jupiter targeting trajectory like this maybe once every few thousand years. We've only been looking for a few decades. The fact that we've spotted one already is either remarkable timing or an indication that Jupiter targeting trajectories are more common than random statistics would suggest. Why would they be more common? That's the question that leads into uncomfortable territory. If interstellar objects are purely natural, ejected randomly from other star systems by gravitational interactions, their trajectories through our solar systems should be essentially random. Some would pass near Jupiter by chance, most wouldn't, and the distribution should follow predictable patterns based on orbital mechanics and the geometry of the solar system. But what if not all interstellar objects are random? What if a small percentage, even a very small percentage, are directed aimed at targets of interest, like giant planets with icy moons? That would change the statistics. You'd still see mostly random trajectories, but occasionally you'd see one that looked too perfect, too aligned, too unlikely to be coincidence. This is the hypothesis that mainstream science rejects, but can't quite dismiss entirely. The idea that some interstellar objects might be probes or couriers sent by unknown civilizations for unknown purposes, traveling for millions of years on carefully calculated paths. It sounds like science fiction. It probably is science fiction, but the mathematics of 3 Atlas's trajectory make it hard to completely ignore the possibility. Comparison with the previous interstellar visitors adds context. Oumuamua, the first confirmed interstellar object, had a highly unusual shape, either elongated like a cigar or flat like a pancake, and exhibited non-gravitational accelerations that couldn't be fully explained by normal cometary outgassing. It also showed no coma or tail, no obvious signs of volatile sublimation, which made the acceleration even harder to explain. Some scientists, again including Avilobo, suggested it might be an artificial light sail, a thin sheet of material pushed by sunlight. Therminstream explanations settled on exotic ice compositions that could sublimate without producing visible tails. Thought his remained controversial. 2I Boris, by contrast, was clearly Acomet. It had a normal coma, a normal tail, normal spectroscopy showing water and dust and all the things you'd expect. Its trajectory was hyperbolic, confirming interstellar origin, but it behaved exactly like comets from our own solar system. No anomalies, no mysteries, just a dirty snowball from another star doing exactly what dirty snowballs do when they get near the sun. 3 Atlas falls somewhere between those extremes. It has country features, a coma and tail outgassing that looks at least superficially normal. But it also has the chemical oddities, the trajectory alignment, the persistent jets that might or might not be steering it. It's too active to be like Oumuamua, too strange to be like 2I Borisov. It occupies an uncomfortable middle ground where natural explanations require stretching our understanding of what's possible, while artificial explanations sound absurd but can't be ruled out entirely. The other factor that matters is inclination, the angle between the object's orbital plane and the ecliptic, the plane where most planets orbit. 3I Atlas approaches at a moderate inclination, not perfectly aligned with the ecliptic, but not wildly tilted either. This is significant because objects ejected randomly from other star systems would have random inclinations distributed evenly across all angles. But if you wanted to target planets, you'd aim for low inclination approaches because that's where the planets are. Most of our solar system's mass and interesting features lie close to the ecliptic plane. The fact that 3 Atlas is approaching at an angle that allows close interaction with Jupiter suggests either coincidence or targeting. There's no middle ground. Either it randomly happened to arrive at an angle in time that places it near Jupiter, or it was sent on that trajectory deliberately. The mathematics don't allow for much gray area between those options. Scientists working on the problem are doing what scientists do, building models, refining observations, checking assumptions, looking for natural mechanisms that could explain the data and their finding possibilities. Anisotropic outgassing, where jets fire preferentially from one hemisphere of the nucleus, could create persistent thrust in particular directions. Rotation states that happen to align active regions with the Sun at optimal times could generate the observed accelerations. Statistical clustering of interstellar object trajectories due to the Sun's motion through the galaxy could make Jupiter encounters more common than purely random models suggest. None of these explanations are fully satisfying yet, but they're plausible, they're natural. They don't require invoking intelligence or technology or intentionality. And in science, we favor natural explanations until they're exhausted, because the alternative opens doors that are very difficult to close again. But every scientist working on this knows, even if they don't say it out loud, that if the natural explanations don't quite work, if the numbers don't quite add up, then we're left with a question we're not prepared to answer. Could an interstellar object deliberately steer itself toward Jupiter? And if it could, what would that mean for everything we think we know about life and intelligence in the galaxy? The steering hypothesis remains speculative, unlikely, relegated to the fringes of serious discussion. But it's there lurking in the equations, visible in the trajectory plots, impossible to completely dismiss. And as March 2026 approaches, as 3I Atlas continues its carefully plotted course toward the giant planet, the hypothesis becomes harder to ignore because whether the alignment is coincidence or design, the result is the same. An interstellar visitor carrying unknown materials will pass through the Jovian system at close range, interacting with the moons and magnetosphere in ways we can observe but might not fully understand. And if there's even a small chance that interaction is intentional, that this is a delivery rather than a flyby, then we need to be watching very carefully indeed. The mathematics of steering a comet across light years are daunting, but not impossible. And that's what makes 3I Atlas so unsettling. It's doing something that shouldn't happen often, but could happen deliberately. And we don't yet know which one we're witnessing. Part 7, the chemistry that shouldn't exist. Chemistry in space is supposed to follow rules. We understand stellar nucleosynthesis, the process by which stars forge elements from hydrogen and helium through fusion. We understand how supernovae scatter those elements into space, seeding the clouds from which new stars and planets form. We understand how comets and asteroids incorporate those elements during formation, creating ices and rocks that reflect the composition of their birth environment. The chemistry should make sense. It should tell a coherent story about where an object came from and how it formed. The Theresi Atlas is telling a story that doesn't quite fit any narrative we know. The first chemical oddity that caught attention was the carbon dioxide to water ratio. Early spectroscopic observations showed that Theresi Atlas was releasing approximately 8 times more carbon dioxide than water vapor, measured by comparing the strengths of emission lines from each molecule. This is unusual but not unprecedented. Some comets from the Kuiper belt, the distant region beyond Neptune, show elevated CO2 ratios because they formed in extremely cold environments where carbon dioxide ice is more stable than water ice. But 8.1 is extreme even by those standards. Water ice dominates most comets we've studied because water is simply abundant in the universe. Oxygen is the third most common element after hydrogen and helium, and it readily combines with hydrogen to form water. Carbon dioxide requires carbon, oxygen, and specific temperatures to condense. Finding an object where CO2 dramatically outweighs water suggests formation in a very cold, carbon-rich environment, possibly in the outer regions of another star system, where conditions differed significantly from our own Kuiper belt, but the real alarm came with the nickel detection. Spectroscopic observations in late 2025 revealed emission lines characteristic of nickel atoms in the coma of Theresi Atlas. That alone wouldn't be shocking. Metals are present in comets trapped in dust grains released when ice sublimates. What was shocking was the strength of the nickel signal relative to iron, which was barely detectable or absent depending on which observations you trust. In normal cosmic chemistry, nickel and iron are intimately associated. They're produced together in stellar nuclear synthesis. They condense together in planetary form. They remain mixed in dust. The ratio of iron to nickel in the Sun, in Earth, in meteorites, in asteroids is fairly consistent, roughly 10.1 or more. Finding nickel without comparable iron is like finding bread without flour. It suggests the iron was removed, or the nickel was concentrated through some process that doesn't occur in standard comet formation. Some researchers have proposed that nickel tetracarbonyl could explain the observations. This is a volatile compound, where nickel atoms bond with carbon monoxide molecules, creating a substance that sublimates at very low temperatures. Nickel-carbon forms under specific conditions involving nickel metal, carbon monoxide gas, and moderate pressures. On Earth, it's used in industrial processes to purify nickel. In space, it's almost never seen naturally because the conditions required for its formation and preservation are extremely rare. If Theresi Atlas contains nickel carbonyl, that raises immediate questions. How did it form? Nickel carbonyl requires metallic nickel exposed to carbon monoxide, which implies either unusual surface chemistry on a metal-rich body or some kind of processing that concentrated nickel and carbon monoxide together. Either scenario fits well with our understanding of how comets form naturally in star systems. The speculative explanation that nobody wants to discuss seriously is that nickel carbonyl could be manufactured. It could be a deliberate component of the object's composition, placed there for a purpose. Maybe as a propellant, since nickel carbonyl decomposes at relatively low temperatures and could provide gentle thrust. Maybe as a catalyst for chemical reactions intended to occur when the material reaches its destination. Maybe as a signature, a marker that says this object is not entirely natural. These ideas sound ridiculous until you remember that we're already observing chemistry that doesn't quite make sense. We're already seeing gradients and compositions that challenge natural formation models. The question isn't whether Theresi Atlas has unusual chemistry. That's established. The question is whether that chemistry is extremely unusual, natural variation, or something else entirely. The morphological features add another layer of mystery. Anti-tails, the structures that appear to point toward the Sun rather than away from it, have been observed in Theresi Atlas at multiple times during its approach. Anti-tails can form naturally through perspective effects when Earth crosses the plane over comet's orbit, causing us to see the dust trail edge on. But the anti-tail features in Theresi Atlas persisted and evolved in ways that suggested active dust, release with unusual geometry, possibly jets firing in multiple directions, or dust particles with unusual optical properties that scatter light differently than expected. Observers also noted that the coma The fuzzy cloud of gas and dust surrounding the nucleus had an asymmetric structure that didn't align perfectly with the expected sunward anti-sun axis. Most comets develop combs and tails that point directly away from the sun because that's where radiation pressure pushes the dust. Seeing asymmetry suggests either rotation carrying active regions through different orientations or multiple active regions firing simultaneously in different directions. All of these features, the high CO2 ratio, the nickel without iron, the persistent anti-tails, the asymmetric coma, they each have potential natural explanations when considered individually. Maybe 3I Atlas formed in a very unusual environment around a carbon-rye star. Maybe it experienced processing by interstellar radiation during millions of years of travel that altered its surface chemistry. Maybe it's rotating in a way that creates the observed jet patterns. Maybe our observations are contaminated by instrumental artifacts or misinterpretations. But when you stack all the anomalies together, when you combine the trajectory that targets Jupiter with the chemistry that doesn't quite fit any natural model, with the morphology that suggests complex outgassing patterns, you start to get a picture that's difficult to reconcile with a simple interstellar comet just passing through. Some scientists have pointed out that we've only studied 3 interstellar objects in detail: Permuau 2I Borisov and 3I Atlas. That's an absurdly sample size. We don't know what's normal for the interstellar population. Maybe they're all weird in different ways. Maybe the chemistry of other star systems is far more diverse than we've imagined. Maybe we're just seeing natural variation and interpreting it as anomalous because we're used to our own solar system's compositions. That's a fair point, and it's the one that most mainstream scientists hold to. We need more data. We need to study more interstellar objects before we can say what's typical and what's genuinely strange. Jumping to conclusions based on 3 examples, one of which was probably an artificial light sail according to Avibe, one of which was a normal comet, and one of which is 3 Atlas doesn't give us enough information to make strong claims, but time is a luxury we might not have. 3 Atlas is approaching Jupiter now. If its chemistry matters, if the materials it's carrying could interact with the Jovian moons in significant ways, then we need to understand that chemistry before the encounter, not years afterward. When we've gathered more statistics on interstellar object compositions, the spectroscopic observations continue every clear night. Telescopes around the world point at 3I Atlas, splitting its faint light into spectra, looking for emission and absorption lines that reveal the molecules and atoms present in its coma. Teams are specifically hunting for organic compounds, the carbon-based molecules that could serve as precursors to life. Amino acids, nucleotides, complex hydrocarbons, anything that suggests this object carries more than just simple ices and rock dust. So far, the data are incomplete. Detecting complex organics in a comet coma is extraordinarily difficult. The molecules are present in tiny quantities, often fragmented by solar radiation before they can be measured, mixed with overwhelming amounts of water vapor and dust that mask their signatures. But the search continues because if 3 Atlas is carrying a cargo of prebiotic chemicals, if it's transporting the building blocks of life from one star system to another, then the chemistry we detect now will be the first evidence of that cargo. The nickel remains the strongest piece of evidence that something unusual is happening. Mainstream explanations are being refined. Models developed to show how nickel could become enriched relative to iron through natural processes. But the models require special pleading, unusual conditions, unlikely scenarios. They're possible, but they're not elegant. They don't feel right. And in science, when the natural explanations start requiring more assumptions than the unnatural ones, that's when people start to get nervous. Not nervous enough to abandon the natural explanations, not yet, but nervous enough to keep looking over their shoulders, wondering if they're missing something, wondering if the universe is trying to tell them something they're not quite ready to hear. The chemistry of 3 Atlas shouldn't exist according to our standard models of comet formation and evolution, but it does exist. We're measuring it. We're watching it evolve as the object moves through the inner solar system. And in a few months, that chemistry will interact with the Jovian environment, mixing with the magnetosphere, potentially depositing onto the moons, initiating reactions that might take decades or centuries to fully unfold. Whether that interaction is a cosmic accident or a cosmic delivery, we're about to find out. The chemistry will tell the story if we're smart enough to read it. Part 8. The Icy Laboratories of Jupiter. The moons orbiting Jupiter are not just rocks. They're worlds unto themselves, each with its own character, its own history written in ice and stone, and the faint traces of geological activity that persist even billions of years after formation. These aren't dead objects. They're dynamic, evolving, shaped by forces that we're only beginning to understand. And beneath their frozen surfaces, some of them hide oceans that might be the most promising places to look for life beyond Earth. Europa is the crown jewel of astrobiological interest. Its surface is young by solar system standards, maybe only 40 to 90 million years old based on crater counts, which is incredibly recent in geological terms. The surface is crisscrossed with fractures, ridges, and chaotic terrain that tell stories of ice tectonics, where the frozen shell cracks and shifts and reforms in patterns that can only be explained by something active happening below. That something is an ocean, a vast body of liquid water sandwiched between the ice shell above and a rocky mantle below. The ocean exists because of tidal heating. As Europa orbits Jupiter, the giant planet's gravity pulls on the moon, squeezing it and releasing it rhythmically as Europa moves through its slightly elliptical orbit. This constant flexing generates heat through friction, the same way bending a paperclip back and forth makes it warm. That heat is enough to melt ice and maintain a liquid ocean, despite Europa being far from the sun where temperatures should keep everything frozen solid. We think Europa's ocean is in contact with the rocky seafloor below, which is crucial for astrobiology. On Earth, life needs more than just water. It needs energy sources and chemical nutrients. Where the ocean touches rock, there's potential for hydrothermal chemistry, reactions between hot rock and water that release energy and create chemical gradients that life can exploit. Earth's deep ocean hydrothermal vents teem with life despite being completely cut off from sunlight, powered entirely by chemistry. Europa might have similar systems. We've detected what might be water vapor plumes erupting from Europa's surface, seen in observations from the Hubble Space Telescope and possibly confirmed by other instruments. These plumes suggest the ocean isn't just sitting there stagnant, it's actively exchanging material with the surface and potentially with space. If those plumes are real, they offer a tantalizing possibility for sampling ocean material without needing to drill through kilometers of ice. A spacecraft could fly through a plume and collect particles for analysis, effectively sampling an alien ocean from orbit. Now imagine what happens if 3IE Atlas deposits material onto Europa's surface or into its tenuous atmosphere during the March 2026 encounter. Dust grains carrying complex organic molecules could settle onto the ice. If those grains eventually migrate through cracks and fissures to the ocean below, they could introduce chemistry that Europa doesn't currently have. Amino acids, nucleotides, lipids, any of the molecular building blocks that life needs, could be delivered by an interstellar courier and find their way into an environment that has everything else required. Liquid water, energy, minerals, time. The chemistry wouldn't create life instantly, but it could catalyze processes that might eventually lead to life. Or if Europa already has life, indigenous organisms that evolved independently. The introduction of interstellar organics could affect those ecosystems in unpredictable ways. We have concepts in biology called horizontal gene transfer, where organisms exchange genetic material and invasive species, where introduced organisms disrupt existing ecosystems. The same principles could apply on cosmic scales. If 3I Atlas is delivering biological precursors to worlds that already have their own chemical evolution underway, Ganymede presents a different but equally intriguing scenario. It's the largest moon in the solar system, bigger than the planet Mercury, and it has a magnetic field generated by a liquid iron core. That magnetic field creates a miniature magnetosphere nested inside Jupiter's larger one, which means Ganymede has some protection from the intense radiation that bathes the inner Jovian moons. Radiation is generally bad for life as we know it, breaking apart complex molecules and damaging biological structures. Ganymede's magnetic shield might make it a more hospitable environment than Europa, despite being farther from Jupiter and experiencing less tidal heating. Ganymede also has an ocean, though its structure is more complicated than Europa's. Models suggest multiple layers of ice with different crystal structures separated by layers of liquid water, all sitting on top of a rocky mantle. This sandwich structure might actually be beneficial for astrobiology, because it creates multiple interfaces where chemistry can occur. Water-touching high-pressure ice has different properties than water-touching rock, and those differences could drive interesting chemical reactions. If 3I Atlas deposits material into Jupiter's magnetosphere, some of that material will eventually spiral down magnetic field lines and impact Ganymede's surface. The Moon's own magnetic field might channel particles toward its poles, creating localized deposition zones where interstellar organics accumulate in higher concentrations. Over time, those deposits could migrate through the ice layers toward the buried oceans, introducing new chemistry into environments that have been isolated for billions of years. Callisto is the outermost of the 4 large moons, orbiting beyond the most intense regions of Jupiter's radiation belts. Its surface is ancient, heavily cratered, showing no signs of geological activity in billions of years. In some ways, Callisto is the boring sibling, the one that didn't get the tidal heating and active geology that makes Europa and Ganymede so interesting. But Callisto might have an ocean too, deep beneath its battered surface. And precisely because it's been geologically quiet, it might preserve ancient materials better than the other moons. Callisto could serve as a repository for interstellar material deposited over the age of the solar system. Every comet that passed through the Jovian system, every dust grain captured by Jupiter's magnetosphere, some fraction of that material ends up on Callisto's surface, where it stays undisturbed by geological recycling. 3 Atlas could be the latest in a long series of deliveries, adding to a collection that spans billions of years. The magnetosphere itself is another player in this story. Jupiter's magnetic field is enormous, extending millions of kilometers into space, trapping charged particles in radiation belts that would be instantly lethal to unprotected humans. That magnetosphere interacts with the solar wind, with particles from Jupiter's volcanic moon Io, with cosmic rays creating a complex electromagnetic environment that's both hostile and fascinating. When 3 Atlas passes through this environment, any dust or gas it releases will become charged and trapped in the magnetic field. Particles will spiral along field lines, bouncing between mirror points near Jupiter's poles, gradually drifting inward or outward, depending on their energy and charge. Some will impact the moons, some will impact Jupiter itself, some will be ejected back into interstellar space. The magnetosphere acts as a sorting mechanism, distributing material based on physical properties in ways that are difficult to predict without detailed modeling. If 3I Atlas is releasing metals like nickel, those metal atoms will become ionized by solar radiation and trapped in the magnetosphere. Nickel ions could inject new chemistry into Jupiter's radiation belts, potentially creating new types of radiation belt particles or altering the behavior of existing populations. We don't fully understand all the chemistry that occurs in planetary magnetospheres, especially when you introduce unusual elements that aren't typically present. There's also the possibility of more direct interactions. If 3 Atlas fragments due to tidal stress as it approaches Jupiter, if it breaks apart into multiple pieces, some of those fragments could impact the moons directly. A comet fragment striking Europa would create a crater, melting gas, potentially exposing or creating temporary connections to the subsurface ocean. Material from the impactor would be injected deep into the ice or directly into the water, bypassing the surface-to-ocean migration process entirely. We've observed impacts on Jupiter before. Comet Shoemaker-Levy 9 broke apart and crashed into Jupiter in July of 1994, creating dark scars in the atmosphere that persisted for months. The impacts released energy equivalent to millions of nuclear weapons visible from Earth through amateur telescopes. If 3 Atlas fragments and some pieces hit the moons instead of Jupiter, we'd see those impacts too. And we'd learn a great deal about both the impactor's composition and the moon's subsurface structure from studying the aftermath. All of these scenarios, dust deposition, magnetospheric injection, direct impact, they represent different pathways for material from 3 Atlas to interact with the Jovian system. Some are more likely than others. Some would have immediate observable effects, while others might take years or decades to become apparent. But all of them share a common feature. They represent opportunities for interstellar material to influence the chemistry and perhaps the biology of worlds that might be on the edge of hosting life. This is why astrobiologists care about 3 Atlas, even though it poses no threat to Earth. Jupiter's moons are natural laboratories for studying the conditions necessary for life. They're places where we might find evidence of independent genesis, life that started from scratch in an environment completely different from Earth. Or they might be sterile chemical systems that have all the ingredients except the spark that initiates biology. If 3 Atlas delivers that spark, if it brings organic molecules or catalysts or even microbial precursors that can survive interstellar travel and deposition onto icy moons, then we might be witnessing something unprecedented. Not the discovery of alien life, but the seeding of alien life. The beginning of a biological experiment that will play out over millions of years in the hidden oceans beneath Europa's ice. The moons won't tell us their secrets quickly, but they'll remember. Whatever happens in March of 2026, whatever material 3 Atlas leaves behind, it will become part of these worlds' chemistry and history. And someday, when we finally send submarines beneath Europa's ice, or drill into Ganymede's layered ocean, or analyze ancient ice cores from Callisto, we might find evidence of a delivery that occurred in the spring of 2026, when an interstellar visitor passed through and left a gift that we're only beginning to understand. Part 9, the hypothesis nobody wants to say out loud. Interstellar objects have always sparked imagination. When Oumuamua was discovered in October of 2017, it took about 3 days before someone suggested it might be artificial. The elongated shape, the tumbling rotation, the lack of a visible coma despite showing non-gravitational acceleration, all of it seemed wrong for a natural object. Avi Lowe, chair of Harvard's astronomy department at the time, published papers suggesting Oumuamua could be a light sail, a thin sheet of material pushed by starlight, possibly sent by an extraterrestrial civilization. The mainstream response was swift and dismissive. Other astronomers proposed natural explanations involving exotic ices that sublimate without producing visible tails or unusual shapes created by tidal disruption or measurement errors that made the object seem stranger than it was. The debate became heated, personal, with accusations of attention-seeking and pseudoscience flying in both directions. Eventually, Oumuamua faded from view too, distant to observe further, leaving behind more questions than answers. 2. Borisov restored some normally discovered in August of 2019. It was clearly a comet behaving exactly as expected, with a normal coma, normal tail, normal composition. It showed that interstellar visitors could be completely ordinary. Just chunks of ice and rock ejected from other star systems through mundane gravitational interactions. The exotic explanations weren't necessary after all. 3I Atlas sits uncomfortably between those extremes. Too active to be like Oumuamua, too strange to be like 2I Boris, and that's bringing the uncomfortable questions back. Javi Lobo has already written about 3 Atlas, discussing the possibility that its trajectory toward Jupiter isn't coincidental. He's careful with his language, always emphasizing that natural explanation should be explored first, but he's also willing to say what other scientists only think privately, that if an advanced civilization wanted to seed life on promising worlds, this is exactly how they might do it. Send objects on carefully calculated trajectories toward giant planets with icy moons carrying organic SU, payloads that disperse during close approaches. Using natural cometry activity as camouflage, the concept is called directed panspermia. The idea that life spreads between star systems, not through random chance, but through deliberate action. It was proposed seriously in the 1970s by Francis Crick, who co-discovered DNA structure, and Leslie Charles-Moore. They suggested that advanced civilizations might send microorganisms or their precursors through space to seed other worlds, either as a way to preserve life against cosmic catastrophes or simply as a form of cosmic gardening. Most scientists consider directed panspermia too speculative to take seriously. We have no evidence that it occurs. No confirmed examples of artificial objects in space. No signals or messages suggesting anyone is out there sending life-bearing payloads around the galaxy. The universe appears silent, empty of technological civilizations despite decades of searching. This silence, sometimes called the Fermi paradox, suggests either that intelligence is extremely rare or that intelligent species don't behave the way we expect. But 3I Atlas doesn't require active intelligence. If it's a seeding vessel, it could have been launched millions of years ago by a civilization long extinct. It could be following programming so simple that calling it intelligent would be generous. Just basic instructions encoded in its structure. Travel towards stars. Use gravity assist to reach giant planets. Disperse payload near icy moons. No communication. No self-awareness, just a machine doing what machines do. The viral claims didn't help the scientific discussion. In late 2025, social media posts began circulating, claiming that telescopes had detected a signal from 3I Atlas, a pattern of pulses at 1420 MHz, the frequency where neutral hydrogen emits radiation, and a wavelength that many SETI researchers consider promising for interstellar communication. The pulses allegedly followed the Fibonacci sequence, a mathematical pattern common in nature, but also recognizable as artificial. None of this was verified. No official observatory confirmed detecting signals. The frequency would be difficult to observe through Earth's atmosphere without specialized equipment. The claims appeared to originate from anonymous sources and spread through channels known for promoting conspiracy theories. Mainstream astronomers dismissed the signal reports as either hoaxes or misinterpretations of natural radio emissions, but the story spread anyway because people want to believe. The idea that we're not alone, that someone or something is out there sending messages or gifts across the void, resonates emotionally even when evidence is lacking. 3 Atlas became part of that narrative, another mystery object that might prove we're not the only intelligence in the cosmos. This creates problems for serious research. When an object becomes associated with conspiracy theories and fringe speculation, scientists become reluctant to study it publicly. Careers can be damaged by association with topics considered pseudoscientific. Funding agencies don't want to support research that sounds like it belongs on late-night radio shows, rather than in peer-reviewed journals. The result is that legitimate questions about 3I Atlas's unusual properties get less attention than they deserve. There's also the dark forest hypothesis, popularized by Chinese science fiction author Lu Cixin. It suggests that the universe is full of civilizations, but they all hide because revealing your location is dangerous. Any civilization that broadcasts its presence might be destroyed by older, more powerful civilizations that see all others as threats. In this framework, probes like 3I Atlas might be reconnaissance, mapping potentially habitable worlds while remaining silent, preparing information for decisions made by entities we can't detect or comprehend. It's fiction, but it captures a real concern that contact with alien intelligence might not be the uplifting exchange of knowledge that optimists imagine. It might be something stranger, more ambiguous, harder to interpret. An object that steers itself toward Jupiter, carries unusual chemistry, behaves in ways that stretch natural explanations, but never confirms or denies intentionality. An object that makes us ask questions we're not ready to answer. Some researchers have quietly asked whether data are being withheld, whether space agencies have information about 3I Atlas that hasn't been publicly released because it's too controversial or ambiguous. There's no evidence of such withholding, but the International Asteroid Warning Network has flagged the object for continuous monitoring, which is unusual for something that poses no threat to Earth. Mission priorities have shifted with proposals to redirect spacecraft toward the object, despite the costs and risks involved. The truth is probably mundane. 3 Atlas is likely a natural interstellar comet with unusual but explainable properties. The trajectory alignment is rare but not impossible. The chemistry reflects exotic formation conditions in another star system. Trajets are active and directional because of rotation and surface features we haven't fully characterized yet. In a few months it will pass Jupiter and continue into space, and we'll have learned something about interstellar object diversity without confirming anything extraordinary. But the fact that we can't completely rule out the alternatives, that's what keeps people wondering. Science deals in probabilities, not certainties. And when the probability of something extraordinary is low but non-zero, when the implications would be profound, if true, we can't afford to dismiss it entirely just because it sounds like science fiction. Sometimes the universe surprises us. Sometimes things that shouldn't exist do exist anyway. 3 Atlas exists. It's heading toward Jupiter, and whether it's a cosmic accident or cosmic gardening, we're about to witness something rare. Part 10, Watching for the Signs. March 16, 2026, is circled on calendars in observatories around the world. That's the date when 3 Atlas makes its closest approach to Jupiter, threading through the gravitational domain of the solar system's largest planet at a distance that allows for significant interaction, but probably not capture. What happens during that encounter depends on factors we can't fully predict. The object's exact mass and density, the strength and direction of its outgassing jets, the details of Jupiter's magnetospheric configuration on that particular day, even the positions of the major moons relative to the object's trajectory. Scientists have outlined 3 main scenarios for what might occur, each with different observable signatures that would tell us what kind of event we're witnessing. The simplest outcome is a clean flyby. 3 Atlas approaches Jupiter, feels the gravitational pull, curves around the planet in a hyperbolic arc, and continues outbound toward interstellar space. This is what happens to most objects that pass near Jupiter. The gravity well acts like a slingshot, changing the object's velocity and direction, but not capturing it. We'd observe normal cometary activity, perhaps enhanced by tidal stress as the object nears periapsis, but nothing unexpected. The coma would expand, the tail would develop further. Spectroscopic observations would show increasing outgassing as solar heating continues. Then the object would fade as it moves beyond Jupiter and heads back to the outer solar system. A flyby would still provide valuable science. Close-range observations during the Jupiter encounter could reveal details about the nuclear size and shape, the jet patterns, the composition of release materials, but it wouldn't mark a major turning point in astrobiology or our understanding of interstellar object behavior. It would be interesting, worth studying, but not transformative. This scenario involves temporary capture or resonance. If 3I Atlas loses enough energy during the Jupiter encounter, possibly through atmospheric drag, if it passes through the upper atmosphere, or through momentum exchange with trapped magnetospheric particles, it could be captured into a highly elliptical orbit around Jupiter. This wouldn't be permanent. Gravitational interactions with the Sun and other planets would eventually eject it again, but it could remain in the Jovian system for months or years. Temporary capture would dramatically increase exposure time. Instead of one quick pass, the object would orbit through the magnetosphere multiple times, releasing material that gets distributed throughout the system. We'd see dust trails developing, forming rings or arcs around Jupiter as particles spread along the captured orbit. The major moons would repeatedly pass through these dust trails, accumulating material on their surfaces in quantities much larger than a single flyby would deposit. Observationally, we track the object's orbit, using radar and optical telescopes, watching for changes that indicate atmospheric interactions or further outging that might alter the trajectory. Spectroscopy would become crucial for identifying exactly what materials are being released and where they're going. Missions like Juno could make multiple observation passes if the spacecraft's orbit can be adjusted appropriately. The third and most dramatic scenario is fragmentation. If tidal forces become too strong as 3 Atlas approaches Jupiter, the object could break apart. We've seen this before with Comet Shoemaker-Levy 9, which fragmented into more than 20 pieces before impacting Jupiter. 3 Atlas is approaching at a different angle and distance, so the tidal stress would be less severe. But fragmentation remains possible, especially if the nucleus is loosely bound or already weakened by internal heating. Fragmentation would create multiple trajectories, each piece following its own path through the Jovian system. Some might impact Jupiter itself, creating atmospheric disturbances visible through telescopes. Others might impact the moons, creating craters and depositing material directly into surface ice or even into subsurface layers. Still others might enter stable or unstable orbits, creating a debris field that persists for years. The signatures of fragmentation would be unmistakable. Multiple bright spots in Jupiter's atmosphere, marking impact sites, sudden changes in the object's brightness as pieces separate, spectroscopic evidence of fresh ice and rock exposed by the breakup. For moon impacts, we might see fresh craters forming in real time or plumes of ejected material rising above the surface before falling back down. Each scenario requires different observing strategies. Ground-based telescopes can provide continuous monitoring of brightness and position tracking the overall behavior. Space telescopes like Hubble and Webb can provide detailed spectroscopy and high-resolution imaging that reveals structure and composition. Radio telescopes can search for any emissions, natural or otherwise, from the object or from plasma interactions in Jupiter's magnetosphere. The deadline for spacecraft maneuvers is mostly past, but there's still potential for observation campaigns, using assets already in the Jovian system. Juno continues its orbit around Jupiter, and while redirecting it to intercept 3 Atlas might not be feasible, adjusting observation schedules to monitor the object during close approach is certainly possible. The spacecraft's instruments can detect changes in Jupiter's magnetosphere that might indicate material injection from the comet. JUICE, the European mission, won't arrive at Jupiter until 2031, too late for the initial encounter. But if 3I Atlas deposits material into the system, if dust settles onto moon surfaces or forms rings around Jupiter, JUICE could study those deposits years later and provide information about the object's composition that wouldn't be available from distant observations. There's also discussion of emergency funding for new observations, reactivating retired instruments, or extending observing time on overdis that 3 Atlas represents a rare opportunity. Interstellar objects don't visit often, and ones that interact closely with major planets are even rarer. Whatever we learn from this encounter will inform our understanding of the interstellar medium, the diversity of objects traveling between stars, and the potential for material exchange between planetary systems. The most important observations will occur in the weeks around March 16th. Before the encounter, we'll watch for changes in activity that might indicate the object is responding to Jupiter's gravitational influence. During the encounter, continuous monitoring will track the trajectory, looking for deviations that indicate capture or fragmentation. After the encounter, long-term observations will determine whether the object remains bound to Jupiter or continues outbound, and whether any material was deposited in observable ways. But we're also watching for something else, something harder to define. We're watching for signs that this isn't just a random flyby, that the object is doing something intentional, that could be steering burns at crucial moments, jets firing when they shouldn't based on solar heating alone. It could be trajectory changes that seem designed to maximize interaction with specific moons. It could be spectroscopic signatures that suggest the release of specific compounds at specific times. Most likely, we'll see nothing like that. 3 Atlas will behave exactly as a natural comet should, and all the speculation about artificiality will be revealed as our tendency to see patterns where none exist. But if we see something unexpected, if the object does something that natural explanations can't easily accommodate, then March 2026 might mark a turning point in human history. The moment we realized we're not alone in the galaxy, or more accurately, the moment we realize the galaxy has mechanisms for spreading life that we're only beginning to understand. The window for observation is limited. Once 3 Atlas moves beyond Jupiter and continues its journey away from the Sun, it will fade rapidly, becoming too dim for most instruments to detect. We get one chance to study this object properly, one chance to answer the questions it raises, and then it's gone. Another interstellar visitor that came and went while we scrambled to understand what we were seeing. The signs will tell the story. We just have to be watching carefully enough to read them. Part 11. The Nickel Signature. 2025 brought a finding that crystallized the strangeness of 3 Atlas into a single element, nickel. The detection came from spectroscopic observations in autumn as the object approached perihelion and its activity increased. Astronomers analyzing the spectral lines in the comet's coma identified emission features characteristic of nickel atoms, which wasn't shocking by itself. Metals appear in comets released from dust grains when ice sublimits. What shocked researchers was the ratio, or rather the lack of one. Iron was barely detectable in normal cosmic materials. Iron outnumbers nickel by factors of 10 or more. They're forged together in stellar cores, scattered together by supernova, condensed together in planetary systems. You don't find one without the other, except under very specific, very unusual circumstances. The implications rippled through the comet science community. If 3I Atlas really does have elevated nickel with depleted iron, it suggests formation conditions unlike anything we've seen in solar system objects. Perhaps it formed around a star with unusual composition, one that produced more nickel relative to iron through atypical nuclear synthesis. Perhaps it experienced some kind of processing during its interstellar journey, cosmic ray bombardment, or chemical weathering that selectively removed iron while preserving nickel. Perhaps we're misinterpreting the spectroscopy, seeing artifacts or contamination rather than real compositional differences. Or perhaps, And this is the explanation nobody wants to voice too loudly. The nickel concentration is deliberate. Industrial processes on Earth can separate nickel from iron. Nickel carbonyl refining creates nearly pure nickel by forming a volatile compound that separates easily from iron. If you wanted to include nickel in an object for specific purposes, catalyzing reactions, or providing trace metals for biological systems, you'd need to concentrate it beyond natural abundances. This is where the speculation becomes difficult to separate from legitimate scientific inquiry. We can measure what's there. We can see that the nickel-to-iron ratio is unusual. But interpreting what that means requires assumptions about formation mechanisms, and those assumptions carry us either toward exotic natural explanations or toward even more exotic artificial ones. The size and age estimates for 3 Atlas make it stand out even among interstellar visitors. Early observations suggested a nucleus potentially several kilometres across, larger than Muamua by considerable margins. The activity level, the amount of gas and dust being released, also suggests a substantial body with significant volatile content. This isn't a small rock tumbling through space. It's a substantial comet-like object carrying materials that accumulated during formation around another star. And the age, that's another mystery. Based on its trajectory and velocity, we can estimate how long 3I Atlas has been traveling through interstellar space. The numbers suggest millions of years, possibly tens of millions. That's an enormous span of time to survive in the harsh interstellar environment, bombarded by cosmic rays, exposed to vacuum, slowly losing volatiles to sublimation, even at the cold temperatures between stars. Objects that old should be dead. Their surfaces processed into inert crusts, their interiors depleted of volatile ices. Yet 3I Atlas is vigorously active, outgassing at rates that suggest fresh ice not far beneath the surface. How does an object maintain that kind of activity after millions of years in space? Natural explanations exist: insulating crusts that protect deeper ice layers, radioactive heating that maintains internal temperatures. But they all require special conditions. The nickel becomes more significant in light of these other anomalies. It's not just own strange feature. It's a strange feature among several strange features. The trajectory that targets Jupiter, the persistent jets, the unusual chemistry, the unexpected activity level for an object of its age. Each anomaly individually might be explicable, but together they paint a picture that makes some researchers deeply uncomfortable. From an astrobiological perspective, nickel isn't just unusual, it's potentially significant. Many enzymes use metal ions as coactors, and nickel plays crucial roles in certain metabolic pathways. Some methanogenic arraea on Earth use nickel containing enzymes to process hydrogen and carbon dioxide into methane. If Europa's ocean or Ganymede subsurface seas develop life, those organisms might need trace metals, including nickel, to build their biochemistry. An interstellar delivery of concentrated nickel could be exactly what those environments need to jump from prebiotic chemistry to actual biology. Is not enough by itself. You'd also need organic molecules and energy sources and liquid water and time. But if all the other ingredients are already present, if Europa's ocean is sitting on the edge of biological complexity, then an influx of catalytic metals from an interstellar source might provide the final push. This is wildly speculative, and most scientists emphasize that point whenever discussing 3I Atlas. We don't know if Europa has prebiotic chemistry. We don't know if the nickel in 3 Atlas will reach Europa's ocean. We don't know if nickel concentration is really as unusual as preliminary observations suggest. We're extrapolating from limited data, seeing patterns that might not hold up under further scrutiny, but the speculation serves a purpose. It helps us think through what we should be looking for. What observations would confirm or refute different hypotheses? If the nickel signature is real and significant, we should see it persist in observations throughout the object's approach. We should detect nickel-bearing dust in Jupiter's magnetosphere after the encounter. We might eventually detect nickel deposits on moon surfaces when future missions analyze their chemistry. The breakthrough isn't just that we found nickel, is that we found nickel in a context that raises questions about larger patterns. 3 Atlas is teaching us that interstellar objects can be far more diverse than we imagined. They can carry unusual compositions, exhibit unexpected behaviors, follow trajectories that seem almost directed. Whether that diversity reflects the range of natural formation conditions across different star systems, or whether it reflects something more purposeful remains to be determined. What we know for certain is that 2025 marked a turning point in how we think about interstellar visitors. They're not just curiosities anymore, not just objects to catalogue and track. They're potential carriers of materials that could affect the future of life in our solar system. And that makes them worth taking seriously, worth studying with every tool we have, worth preparing for even when we don't fully understand what we're seeing. The nickel in 3 Atlas is a clue. What it's a clue to, we'll find out when the object reaches Jupiter and reveals what it's really carrying. Part 12. Redirecting the eye in the sky. Spacecraft weren't built for improvisation. Every mission is planned years in advance. Every trajectory calculated to mil precision. Every instrument schedule optimized for maximum scientific return. You don't just point a probe at something new because it looks interesting. The fuel budgets are too tight, the risks too high, the stakeholder expectations too rigid, except when something like 3 Atlas appears, and suddenly mission planners find themselves reconsidering everything they thought was fixed. Juno arrived at Jupiter on July 4, 2016, and has been returning spectacular data ever since. The spacecraft's polar orbit takes it skimming just 5,000 km above Jupiter's cloud tops at closest approach, then swinging out to distances of over 8 million kilometers before returning. This orbit was carefully designed to minimize radiation exposure while maximizing scientific observations of Jupiter's atmosphere, magnetic field, and gravitational structure. Changing that orbit isn't a casual decision. The proposal to redirect Juno toward 3 Atlas emerged in summer of 2025, shortly after refined trajectory calculations showed the object would pass relatively close to Jupiter. Engineers calculated that a burn executed on September 9th could alter Juno's orbit enough to bring the spacecraft near the comet during its March 2026 encounter. The required delta V would be approximately 2.675 km/s, substantial, but potentially within the spacecraft's remaining fuel capacity. The debate within the mission team was intense. Juno has already exceeded its primary mission lifetime by years, operating on extended funding that could end at any time. Using precious fuel reserves for a comet intercept would limit future options for Jupiter science. If the intercept failed, if 3I Atlas turned out to be less interesting than hoped, the mission might end having sacrificed proven scientific return for a gamble on something uncertain. But the counterargument carried weight, too. 3 Atlas represents a once-in-a-lifetime opportunity. We might never again have a spacecraft positioned to intercept an interstellar object at close range. The data Juno could collect, direct measurements of the comet's composition, its magnetic properties, if any, its interaction with Jupiter's magnetosphere, would be invaluable for understanding interstellar object nature and the potential for material transfer to the Jovian moons. The decision process involves more than just the immediate science team. NASA management must weigh competing priorities, budget constraints, programmatic risks. Congressional oversight committees want assurance that taxpayer-funded missions deliver expected results. International partners who contributed instruments to Juno have their own interests and expectations. Changing course isn't just a technical decision, it's a political and financial negotiation. As of late 2025, no final decision had been publicly announced about Juno's trajectory. The September 9th deadline for the optimal burn passed without confirmation that the maneuver occurred. This ambiguity might reflect ongoing deliberations, or it might indicate that the decision was made privately to avoid public pressure. Either way, space agencies sometimes prefer to operate quietly on controversial matters, releasing information only when outcomes are certain, even without redirecting Juno. The spacecraft can contribute observations during the 3I Atlas encounter. Its instruments can monitor Jupiter's magnetosphere for disturbances that might indicate material injection from the comet. Changes in plasma density, shifts in magnetic field geometry, enhanced radiation belt populations. All of these would suggest that 3I Atlas is depositing material into Jupiter's environment even from a distance. The JUICE mission adds another layer to the deep space probe story. Launched by the European Space Agency in April of 2023, JUICE is currently on a complex trajectory that uses multiple Earth and Venus gravity assists to eventually reach Jupiter in July of 2031. That arrival date is too late for the initial 3 Atlas encounter, but JUICE's mission is specifically focused on Jupiter's icy moons, particularly Ganymede, where it will eventually enter orbit. If 3I Atlas deposits material onto the moons, or creates lasting changes in the Jovian system, JUICE will be perfectly positioned to study those effects years later. The spacecraft carries instruments capable of analyzing surface composition, measuring magnetic fields, penetrating us with radar to map subsurface structure. It could detect nickel deposits on moon surfaces, identify organic compounds delivered by the interstellar visitor, even potentially measure changes in ocean chemistry if the material penetrated deep enough. This represents a new paradigm in solar system exploration. Missions planned years ago, fortuitously positioned to study events that weren't anticipated when the missions were designed. It's accidental synergy, but it demonstrates the value of maintaining diverse observational capabilities throughout the solar system. We never know when something unexpected will occur, and having assets already in place makes opportunistic science possible. The technical challenges of deep space interception remain formidable, even when spacecraft are available.